Okay, frequency. Determine the frequency of the waveform as displayed by an oscilloscope with a vertical sensitivity of 2 volts per division and a time base of 0.5 milliseconds per division. So if we look at this, okay, this is right there, that's my 0 point, right? That's my 0 point. Right there. So we've got an equal, sine waves are equal. So what's happening in the alternation? The positive is happening in the alternation of the negative. And what is happening in terms of time is happening during the on cycle and the off cycle, or the positive cycle and the negative cycle. Okay, so those two are the same, meaning that the amount of time between here at high and here at high is equal to the number, to the amount of time from here at high and here at high. Okay, so let's take a look at what we would do for the frequency. So what we're going to do is we're going to count the time division. So I'm going to count the full boxes. So 1, 2, 3, 4, and 5. So I have 5 time divisions. Each one of those time divisions equals 2.5 milliseconds. Now, the formula for frequency is 1 over time in seconds, not 1 over time in milliseconds. So we have to factor in, what is my time for that cycle? Well, it is however many divisions times the value per division. So 1 over, we know that 2.5 milliseconds divided by 1,000 to get it to its base unit is 0.0025 seconds. And what we're going to do is we're going to say, okay, so my frequency is going to be a function of my divisions times however many that I have here. So 2 milliseconds. So in my calculator, what I'm going to do is I'm going to say, okay, 2.5 milliseconds is equal to 0.0025. And I'm going to get the reciprocal. What I'm going to do is I'm going to get the reciprocal of that. So I'm going to multiply my divisions by my time base and then do the reciprocal of that. So hopefully remember how to do the reciprocal formula. Question number 6. Assuming the vertical sensitivity control is set to 2 volts per division and the time-based control is set to 10 micro, which is 10 to the negative 6th per division, calculate the amplitude of this sawtooth wave. Notice it is a sawtooth. So how do we do that? Well, we're going to take a look at, we're looking at amplitude, so we're looking at the voltage. So we're going to count our divisions. 1, 2, 3, 4, 5, 6, 7, 8. There's 8 divisions, and each division equals 2 volts. So 8 divisions times 2 volts is 16 volts peak to peak. So I can divide that by 2 to give me my 8 volts peak. Because I want to find out what my frequency is here. So if we look at frequency, frequency is 1 over time in seconds. And we're saying that it is 1 microsecond per division. That is 0.00001. And I count over 15 divisions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 divisions. Right? From the time it goes all the way up and then all the way down, I have 15 divisions. So that's going to be 0.00001 times 15 divisions. The reciprocal of that is going to tell me I have 6,666.66 hertz divided by 1,000. So that would be 6.66 kilohertz. Scope number 7. Whoops. Scope number 7. Okay, most oscilloscopes have at least 2 vertical inputs. All of ours do. And what they're used for is you'll have a channel 1 yellow and a channel 2 blue. You're going to use those in this lab to have two waves on your scope at one time. So now this feature is really handy, but you got to really pay attention to what's happening here. Because look, now you're not going to use these attenuator probes. You're going to end up using just the gator clips. So when you look at the drawing, it'll show a gator, it'll show an attenuating probe. It'll talk about being an amplifier probe or attenuator probe. Just discount that. Don't worry about that. You're just going to be using the normal BNC red and black. The red would be this one, and the black would be the common or bond. Okay, so if we look at this, notice this is bonded here and this is bonded here, meaning that those two have to go together because they're bonded internally within the scope itself. So what I mean by that is if we look over here and we see what's happening here, we've got a scope here that is looking at a circuit. So the current is coming through from my function generator. It goes through here, goes through this resistor, and it goes through this contact, through that contact to this resistor, through this contact to this resistor, and then back home. So now look what happens where the scope is connected like this, where the current goes through here, and then this is a bond. So now all of a sudden what's happened? I've short-circuited my circuit here. So that's going to sort of represent itself. If I was to draw that schematically, it would represent itself like this. Look, same deal. Current comes through from the function generator through that first resistor, and it's bonded to ground. Now we have a short circuit. So if you don't see a line come up, it's because you have a short circuit. Scope number 8. Okay, assuming the vertical sensitivity control is set to 0.5 volts per division and the time-based control is set to 2.5 milliseconds per division, calculate the amplitude of the sine wave in volts peak to peak, and volts RMS as well. The formulas I provided on your lab are there for you. So if we look at this, we've got voltage. So we look at the divisions. So how many divisions do we have? 1, 2, 3, 4, 5, 6, 7, 8, and 9. We have 9 divisions. Each division, it says, is set for 0.5 volts per division. So 9 divisions times 0.5 is 4.5 volts peak to peak. I want to get to peak voltage, which means I'm going to divide by 2. So it's going to tell me I have 2.25 volts peak. Remember, peak to peak is just simply the peak here and the peak here. Voltage peak is just from the zero standing point all the way up to there, or from the zero standing point all the way down to here. So it's just half of your voltage peak to peak. Okay, so 2.25 volts peak. Now, determining my RMS value from voltage peak is going to be my voltage peak of 2.25 times 0.7071, which is equal to 1.59 volts RMS. Your meter reads RMS, which is root mean square. Frequency, calculating frequency, we're going to count over all the divisions from the starting as it goes up, all the way down to the negative cycle back to the 0 point again. And we're going to count those divisions. I counted 10 divisions. So, and each division is equivalent to 2.5 microseconds, right? So punching it into the calculator, I would say 2.5 microseconds. I'm going to convert that. I'm going to tell my calculator to convert that so I can use it. So 2.5 to 10. So I use the exponent, 2.5 to the exponent, negative 3 equals 2.5 to the exponent 3 times 10 equals 0.0025. That's my time. Then all I'm going to do is I'm just going to do the reciprocal of that. I'm going to do the reciprocal of that, hit this reciprocal button right here. And it's going to tell me that the reciprocal of that is 40. So it means that I have a frequency of 40. Scope number 9. Okay, we already looked at this stuff here. I'm just going to get rid of this stuff so it's out of our way. Bear with me for a sec as I clean off the board. Okay. Assuming the oscilloscope display has been properly zeroed and the vertical sensitivity is at 2 volts per division, determine the voltage of the battery. To get that up, I don't think it's going to allow me to redo this. I put too much on the slide. Yeah, so it's only going to allow me to get to there. So I can't move this out of the way. So if we look at this, what we're saying is, okay, determine the value of and the polarity of the battery. Well, if I look at this, gee, look at this. If this is my 0 starting point, and this is -2, this is -4, this is -6, it's somewhere around, I don't know, -7, which really tells me you just have, if you have your battery, if you're reading a value on the battery, you're going to put your red on your meter to the red terminal, the positive terminal, right? And you're going to put the black on your meter to the negative terminal. And you're going to get, in this case, 7 volts. But it's going to show up over here as a +7.